Thank you for tuning in this video. My name is Yuan Jiang. In this video, I'm going to share customizable mechanical characterization platform for multi-scale structural materials using image/CAD particle converters and GPU-accelerated Lattice model. After million years of evolution, nature has come out with superior designs of structural and composite materials that can be found across insects, mammals, to plants. These designs often exhibit non-homogeneity, discontinuity, and complex geometry at multiple length scales. Therefore, predicting their mechanical property and responses can be challenging for continuum approaches like finite element methods. Especially becomes computationally expensive for finite element to describe complex structure and materials because the number of elements increases drastically and many assumptions as well as calibrations are required to guarantee numerical convergence. Particle-based method, on the other hand, has been recognized effective tool to simulate the dynamics and fractal behavior of solids with high geometric complexity. Therefore, we propose a customizable platform to first convert 2D image and 3D CAD solid into lattice model and then adjoint solid. Since particle-based methods such as LSM can be slow when a large number of particles are used, we further develop CUDA-C++ lattice remodel code CULSM to accelerate 2D LSM simulations. The idea of image-to-particle is simple. We first arrange particle in 2D triangular lattice. In the next step, we map a particle coordinate to raster image domain. In the final step, we categorize particle types according to the pixel in the image and assign them the corresponding material properties. If we consider the first nearest neighbor case of the lattice model, each particle can be connected up to 6 particles in a 2D model. In a sequential programming, force calculation becomes extremely slow because each particle needs to evaluate up to 6 spring forces one by one. To speed up simulation, we adopt parallel programming for boundary conditions, force calculation, and velocity-valence integrations, which include the particle velocity, position, and acceleration update. The entire integration process is performed on GPU without coping back and forth between CPU and GPU, which saves a lot of time during time integration. If you only care about the final configuration of the model, you can simply just simulate the entire process from the beginning to the end and skip all of the thermodynamics and stress output, which will further save you more time during the time integration process. We compare the final fractal pattern of composite structure predicted by CULSM and LEMS. The fractal patterns are nearly identical for these two programs, but CULSM with one CPU and one GPU can secure 1.5 to 4.4 times speed up compared with LEMS with one CPU to 4 CPUs. To extend our work to 3D cases, we developed OF2Particle to convert 3D CAD solid into particle model. By using our code OF2Particle and AABB tree algorithm supported by CGL, we let the code count the number of intersections between a random ray emanating from particle with the vertices, edges, and the faces of solids. After that, we train down the particle with inverse times of intersections. This allows us to create particle model with complex geometry and topology, or mathematically speaking, an arbitrarily non-convex shape of particle models. Here is demo that we use OF2Particle to create temporal anchorage devices and describe particle intersection by Lagrange's potentials. We then insert the temporal anchorage devices into the solid plate and calculate the force required to penetrate through the plate with different depths and the pilot hole radii. We can see the thicker the plate depth, the greater the force required for insertion. On the other hand, the radius of a hole affects the plate stiffness for the temporal anchorage devices to penetrate through. I would like to thank my advisor, Professor Shui Zhang at National Taiwan University, as well as most NCHC and NCRE centers in Taiwan for their financial and facility supports. Thank you very much for listening, and I'm happy to answer any questions online or by email.